Okay, we'll start in about 2 minutes. Okay, we'll start at 8 a.m. That's just in a few seconds. Go ahead and sign in. All right, it's 8 o'clock already. Today we'll start section 5.2. On Monday we'll also be in 5.2. This has to do with properties of exponents. I emailed the quiz 4, the home quiz 4 earlier this morning, so that will be due at midnight tonight. Hey, properties of exponents. If b does not equal 0 and if n is a positive integer, then b raised to the power n can be written as b with the exponent n. So we read that as b to the nth power or b raised to the power n. But n is in the position of the exponent. It's a raised number. Okay, so the base of the term b to the power n is b, and the exponent of b to the power n is n. When n is a positive integer, and just as a reminder, the positive integers are 1, 2, 3, 4, and so on. Then b raised to the power n is shorthand for b times b times b and so on, where b is a factor n times. Okay, so the exponential notation is a convenience because it takes a short time to write a base number raised to an exponent, but what it represents, if you were to write out what it represents, it could take some time. So for example, 2 raised to the power 4, that means 2 times 2 times 2 times 2. The exponent 4 is not very big, but you can see that 2 to the 4th is less complicated than writing out 2 times 2 times 2 times 2. And then we simplify when it's easy enough to do. 2 times 2 times 2 times 2 is just 16. 3 raised to the power 2, this one isn't so bad. This just means 3 times 3. And 3 times 3 is 9. 5 to the 3rd, that means 5 times 5 times 5. 5 times 5 is 25, and then 25 times 5 is 125. Okay, then 7 raised to the power 10. I'll just write down what that means. This is a shorthand notation for writing 7 times 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 7. So it's a pretty big number because if you multiply those out, well, it's going to be a large number. But perhaps you'll be convinced that writing 7 to the power 10 is much more convenient than writing out a product of n factors of 7. Okay, there are properties of exponents. So here we'll let a and b be non-zero real numbers, and we'll let m and n be integers. So here's the product rule for exponents. If we multiply a raised to the power m by a raised to the power n, we can simplify that and write it as a to the m plus n. You don't really need to remember the terms for the properties. What you do need to remember is the properties, how they work themselves. So just note that when we're multiplying here, the base number is the same in both of those exponential terms. The base number is a. So a raised to the power m equal times a to the power n is a to the m plus n. Okay, if you have something like this, 2 to the third times 2 to the second, we can write it using this property. 2 to the 3 plus 2, or 2 to the fifth. And 2 to the fifth is 32. When simplifying 2 to the third times 2 to the second, it might be easier to first simplify 2 to the third. 2 times 2 times 2 is 8, times 2 to the second, which is 2 times 2, so 8 times 4 is 32. But just to illustrate this product rule, 2 to the third times 2 to the second, if you think of 2 to the third as 2 times 2 times 2, and then we're multiplying that by 2 to the second, which is 2 times 2, then you can see that there are 5 factors of 2. So 2 times 2 times 2 times 2 times 2 is 2 to the fifth. Okay, the quotient rule, this property of exponents, if you have a raised to the power m divided by a raised to the power n, that simplifies to a raised to the power m minus n. Okay, so in this example, 3 to the fourth divided by 3 to the third, if we apply this property, we can write it as 3 to the 4 minus 3, and then 4 minus 3 in the exponent is just 1, so 3 to the first, which is 3. Just to illustrate what's going on here, 3 to the fourth in the numerator is 3 times 3 times 3 times 3. And in the denominator, 3 to the third is 3 times 3 times 3. And you know from fraction arithmetic if you're dividing a product by another product, you look for common factors. So 3 divided by 3 equals 1, so those cancel. And then we have another 3 divided by 3 that cancels. And then a third pair, 3 divided by 3. And so this simplifies to 1 is a factor of everything. You can think of this as 3 over 1, but 3 divided by 1 is 3. When exponents are large, using this property will come in handy. When the exponents are relatively small, like these ones, you can simplify those using other techniques besides the properties of exponents. But you'll want to know the properties of exponents, especially when exponents are large numbers. A negative exponent, if we have a raised to the power negative n, then that's equal to 1 divided by a to the positive n. Okay, here's an example. 5 raised to the exponent negative 2. First, we write it as 1 divided by 5 raised to the positive 2. And then 5 to the second is 5 times 5, so we get 1/25. Generally, when you're working in the software and also when you're taking quizzes and tests, you'll want to not leave an answer with a negative exponent. So that will be part of the simplification process. Make sure that the exponents are not negative in the final answer. And if they involve numerical bases, a numerical base is like 5, then you'll want to evaluate that part. 5 to the second is 25. Hey, the 0 exponent, remember a is the base number, and we're assuming a is non-zero. So a non-zero number raised to the exponent 0 is always equal to 1. And so in this example, 7 raised to the power 0, that equals 1. So let's prove the 0 exponent property. And we'll use other properties in the process. So in this little proof, let's let a be a number that's not equal 0. So let a not be 0. And let m be an integer. So an integer, the positive integers are 1, 2, 3, 4, and so on. 0 is an integer. And then the negative integers are -1, -2, -3, and so on. Okay, so what do you get when you divide a non-zero number by itself? So a raised to the power m is non-zero because a is not 0, and we're dividing it by itself. So what do you get when you divide a number by itself, a non-zero number by itself? You get 1, right? That's the answer. a to the m divided by a to the m is 1. Okay, if I use the quotient rule to simplify a to the m divided by a to the m, so use the quotient rule. To simplify a to the m divided by a to the m. Okay, so here's the quotient rule. The quotient rule says a to the m divided by a to the n is a to the m minus n. In this special case, a to the m divided by a to the m, using the quotient rule, is equal to what? If I apply the quotient rule, then I write the base number a, and then the exponent is m, which is the exponent from the numerator, minus n, which is the exponent from the denominator. So what I have here is not exactly the same as a to the m over a to the n, but the property still applies. So using the quotient rule, what's a to the m divided by a to the m?
A to the m minus m.
Yeah, a to the m minus m. But we know from arithmetic that m minus m is what? It's 0. So we get a to the 0. So on one hand, we all agreed that this non-zero number divided by itself, a to the m divided by a to the m equals 1. And using the quotient rule, we can also say that a to the m divided by a to the m is equal to a to the 0. So we conclude, since a to the m divided by a to the m equals 1, and a to the m divided by a to the m equals a to the 0, we can conclude that a to the 0 equals 1. Okay, so that proves the 0 exponent property. While we're on this page, let's take a look at the negative exponent. Okay, so if I start with, look this up a bit. If I start with 1 over a to the n, so I'm starting with the right side of the negative exponent property. So 1 over a to the n is equal to, let's see, what's another way I can express the number 1 in the numerator? Yeah, I'm thinking of what we just did in the previous example. I can replace 1 with a to the 0, right? So 1 over a to the n is equal to a to the 0 divided by a to the n. And then if I apply the quotient rule to this term, a to the 0 divided by a to the n, according to the quotient rule, this is a to the 0 minus n. And what's 0 minus n? Negative n. Negative n. 0 minus n is just negative n, so I get a to the negative n. So this, in effect, proves the negative exponent property. You can write 1 over a to the n as a to the negative n, or vice versa, which is normally what we do. A to the negative n is equal to 1 over a to the positive n. Okay, so all of these properties are consistent, and you can use some of the properties to explain other properties. Hey, there are more properties of exponents. Okay, so let a and b be non-zero real numbers, same as before, and also let m and n be integers. The power property So if we have a raised to the power m, and if that entire expression is raised to the power n, then this is a to the m times n. So we're just multiplying the exponents. Okay, so here's an example. 2 to the third to the second. We can just simplify that. The first part would be to multiply the exponents 2 times 3. So the exponent becomes 6. And then we can evaluate 2 to the 6th. 2 times 2 times 2 times 2 times 2 times 2 is 64. Okay, another way to look at that, if you have something squared, or something to the second power, so here we have 2 to the third, which is raised to the second power. That just means 2 to the third times 2 to the third. And then we can use the property that the product rule property. 2 to the third times 2 to the third is 2 to the 3 plus 3. And 3 plus 3 is 6, so we get 2 to the 6th. Okay, so there's often multiple ways that you can go about finding the result. So since we're on the subject of finding results, to simplify 2 to the third raised to the second, you can first begin with simplifying 2 to the third. So I'll rewrite this, 2 to the third to the second. I can simplify what's inside the parentheses. 2 to the third is 2 times 2 times 2, which is 8. And then 8 to the second is 8 times 8. And we get 64 that way also. Okay, so this is just to show you that generally there's not just one way to go about simplifying something with exponents. Okay, the next property, product to a power. If we have a times b, that's a product inside parentheses, and the entire product is raised to the power m. So we can write this as a to the m times a to the n. So to reiterate a little bit more about this, inside the parentheses, we can think of A as A to the first, and B as B to the first. And so when we remove the parentheses, we have to multiply this exponent m times each of those exponents. So it's a to the m times 1 times b to the m times 1. My property up here is not correct. This should be b to the m. So I'll restate this over here. We have a times b to the m. That should be a to the m times b to the m. Yeah, and this one, when numbers are involved, instead of just variables or letters, there are multiple ways to go about simplifying. If we have 2 times 5 to the third, we can apply this property and write it as 2 to the third times 5 to the third, and then simplify it. 2 to the third is 8. 5 to the third, 5 times 5 times 5 is 125. And then 8 times 125 is 1,000. Another way to do it, if we have 2 times 5, if that product is raised to the third, we can multiply 2 times 5 inside the parentheses first. 2 times 5 is 10. And then 10 to the third that means 10 times 10 times 10, which is 1,000. Okay, the next property, a quotient to a power. A quotient is like a fraction. It's a rational expression, meaning that it's the ratio of two things. So there's something in the numerator and something in the denominator. So we have a quotient, a over b raised to the power m. And so that will simplify to a to the m in the numerator divided by b to the m in the denominator. Okay, so in this example, the fraction 3/5 raised to the 4th power, if we apply this property directly, in the numerator we'll get 3 to the 4th, and in the denominator 5 to the 4th. And we can simplify these. In the numerator, 3 to the 4th, that's just 3 times 3 times 3 times 3. So how much is that?
81.
Yeah, it's 81. 3 to the 4th, 3 times 3 times 3 times 3 is, I'll go ahead and write it, 3 times 3 times 3 times 3. In the denominator, 5 to the 4th is 5 times 4, 5 times 5 times 5 times 5. Another way to think of 3 times 3 times 3 times 3 is to think of it as 9 times 9, because 3 times 3 is 9. 9 times 9 is 81. And then 5 to the 4th, 5 times 5 is 25. And then if we multiply 25 times 25, we get 625. So I'll make a passing comment. We started with a base number that is a fraction, 3/5. And notice that 3/5 is in lowest terms already. So if you raise a fraction that's in lowest terms to a positive exponent, positive integer exponent, then the resulting fraction will also be in lowest terms. You can see that here when you multiply the fractions out. The greatest common factor of the numerator and the denominator is 1, so there aren't going to be any cancellations. So this will automatically be a fraction in lowest terms, in case you're wondering. Okay, some more to do with negative exponents. So on the first page, we had this property, a to the negative n equals 1 over a to the positive n. Well, this one also works. If you have 1 over a to the negative n, that's equal to a to the positive n. So we can prove this in a couple of steps. If I start with 1 over a to the negative n, just like we did earlier, what's another way to write 1? A to the 0, so a to the 0 is equal to 1. So a to the 0 divided by a to the negative n. And then if we use the quotient property that we saw on the first page, a to the power 0 divided by a to the power negative n is a to the 0 minus negative n. But 0 minus negative n is 0 plus n, and 0 plus n is n. So now we're convinced that 1 over a to the negative n is just a to the n. Hey, this example is very useful. This is another property. If you have a fraction a over b that's raised, the entire fraction has the exponent negative n, then you can reciprocate the fraction. The reciprocal of a over b is b over a, and then change the exponent to positive n. And then when you have a positive exponent, you can, on a fraction, you can apply the quotient to a power property and get b to the n over a to the n. Okay, a couple of examples. If you have 1 over 7 to the negative 2, that's equal to 7 to the positive 2. And 7 to the positive 2 just means 7 times 7, or 49. Okay, over here we have a fraction 5/4 raised to the exponent negative 2. So if we apply the property up here, first we write the reciprocal of 5/4, which is 4/5. We change the exponent to positive 2. And then we can simplify further, because the fraction 4/5 to the exponent 2 is 4 to the second in the numerator and 5 to the second in the denominator. And then 4 to the second is 16 in the numerator, and 5 to the second is 25 in the denominator. Okay, we'll look at some more examples. Hey, these next couple of examples are important to pay attention to. they don't look very, very complicated, but you can avoid trouble if you make sure that you catch all of the details. Okay, so this first one, we have negative 3 to the second. Okay, but what it means is, it means the negative of 3 to the second. So the exponent 2 applies to 3. It doesn't apply to negative 3. So this is equivalent to negative 1 times 3 to the second. Normally we don't want to have to write this, but that's what it means. And then if you remember the order of operations in arithmetic, you evaluate exponents before you multiply. So negative 1 times 3 to the second is negative 1 times 9, which is negative 9. Okay, so the negative of 3 to the second is negative 9. So a couple of things that can be said. The number negative 3 is not in parentheses. So I'll just say the exponent 2. The exponent 2 applies to the base number 3. Okay, the example to the right has a different meaning than this example on the left. This time, the exponent 2 applies to the number negative 3 because negative 3 is in parentheses, so it's the number negative 3 that's raised to the exponent 2. So one way to interpret this is the number negative 3 to the second is the number negative 3 times negative 3. And negative 3 times negative 3 is positive 9. It's a subtle difference. Not really subtle if you just remember the order of operations. But it's an important thing to remember. So an engineer could collapse a dam if he forgot that. Well, I suppose it could happen. Okay, the next examples, here we have negative 3 to the third. And over here we have negative 3 to the third. So when I read those, they sounded pretty much the same, but they mean different things. So to elaborate on the left, this means the negative of 3 to the third, which is like multiplying negative 1 times 3 to the third. So negative 1 times 3 times 3 times 3. So we're going to get negative 27. Negative 1 times 3 times 3 times 3 is negative 27. Okay, this expression on the right, the number negative 3 to the third, that means negative 3 times negative 3 times negative 3. and we get negative 27 again, but we get negative 7 as the final answer, but not for the same reasons. So sometimes you can luck out and get the right answer for the wrong reason. But if the exponent is even, like 2, then you can get yourself into trouble by not remembering the smaller details. Okay, we'll apply the properties involving expressions with variables instead of just numbers. But the properties themselves have variables in them. So these won't be too bad. So this one, simplify x to the third times x to the fourth. The base is the same. The base is x, and we're multiplying. So x to the third times x to the fourth is x to the 3 plus 4, which is x to the 7th. And since x is a variable, we can't simplify any further. The next example, x to the 7th divided by x to the 2nd. This is x to the 7 minus 2, or x to the 5th. Another way to look at this, you can think of x to the 7th over x to the 2nd. Since the denominator is x to the 2nd, we can rewrite the numerator x to the 7th by writing x to the 5th times x to the 2nd, and then divided by x to the 2nd. And then x to the 2nd divided by x to the 2nd equals 1, so we just get x to the 5th. You don't have to go into that much detail, but doing so can, if you happen to forget a particular property of exponents, you can use other properties to help remind you of how that property works. Okay, the next example, we have y to the 3rd over x to the 4th, and that entire rational expression or fraction is raised to the exponent -4. So we don't want negative exponents. So we'll write down the reciprocal of y to the 3rd over x to the 4th. So it's x to the 4th over y to the 3rd. And then we change the exponent to +4. Okay, so we can simplify further, and we can do so directly. So in the numerator, we have x to the 4th to the 4th. So if we multiply the exponents, 4 times 4, we get x to the 16th. And then in the denominator, we multiply the exponents, 4 times 3, so the exponent on y in the denominator is 12. If you don't remember that maneuver, then you can use a more fundamental property. If you have something raised to the 4th power, you could write this. You might not enjoy doing this, but you could write it as x to the 4th over y to the 3rd times x to the 4th over y to the 3rd times x to the 4th over y to the 3rd times x to the 4th over y to the 3rd. And then if you multiply the numerators, x to the fourth times x to the fourth is x to the 4 plus 4, or x to the 8th. And then x to the 8th times x to the 4th is x to the 12th. And x to the 12th times x to the 4th is x to the 16th. Right? All I did was add the exponents because I'm multiplying. And then do the same thing in the denominator, y to the third times y to the third times y to the third times y to the third is y to the 3 plus 3 plus 3 plus 3, which is y to the 12th. Okay, the next one, here we have in parentheses x to the second over 2, and it's raised to the power 2. So you can think of 2 in the denominator as 2 to the first power. And then we apply this quotient to a power property. We're going to multiply the outer exponent 2 times each of those exponents. So in the numerator, we get x to the 2 times 2, or x to the 4th. And in the denominator, we get 2 raised to the 2 times 1, or 2 to the second. And then 2 to the second in the denominator simplifies to 4. 2 to the second is 2 times 2. In the next example, we have 4 times x to the third times y to the second, which is all raised to the negative 4. So I'll remind you of the property that we're going to use. If we have a to the negative n, we write that as 1 over a to the positive n. What we have looks more complicated than just a to the negative n, and it is, but it's still the same property that we're going to apply. We'll write this as 1 over this quantity, 4x to the third, y to the second, to the positive 4. Okay, so inside the parentheses, think of that as 4 to the first times x to the third times y to the second. And when we apply this outer exponent 4, we're going to multiply this exponent 4 times each of those 3 exponents. So we get 4 to the 4 times 1, or 4 to the 4th. And then x to the 4 times 3, multiply the exponents, we get x to the 12th. And then y to the second to the 4th is y to the 4 times 2, or y to the 8th. And then 4 to the 4th is just 256. So we'll write 1 over 256 times x to the 12th times y to the 8th. Okay, we have a couple of minutes left. We'll get started. I'll just start the next problem. We're going to be in this section again on Monday. Okay, so this one's involves a product. We're just multiplying a bunch of things together. And we have 3 negative exponents. So in the end, we want our answer to have no negative exponents. And we want each variable to appear only once with a and we want it to have a positive exponent. Okay, so since we're just multiplying, we can remove the parentheses. We can write it as m times n to the negative 3 times m to the negative 5 times n to the negative 2. And when we multiply numbers, these just represent real numbers, we can switch the order of the factors, if that helps. So I'm going to rearrange the factors, and I'm going to put an exponent on m to the first, and then times m to the negative 5, and then times n to the negative 3 times n to the negative 2. And then apply the product property for the variable m. M to the first times m to the negative 5 is m to the 1 plus negative 5, or m to the negative 4. And then we're multiplying that by n to the negative 3 times n to the negative 2. But that's just n to the negative 3 plus negative 2, which is negative 5. And now we're just one step away. M to the negative 4 is 1 over m to the positive 4. N to the negative 5 is 1 over n to the positive 5. And then when we multiply those, we can write it as 1 over m to the 4th times n to the 5th. Okay, we're out of time for today. We'll do the rest of these problems on Monday, plus a bunch more after that.